Hi, everybody. It's Miss Weeson, and this is the second podcast in Unit 3. We're at the top of page 4, and today in this podcast, we're going to learn about how intermolecular forces can actually predict the various types of physical properties, and you'll see some of those physical properties listed here in your notes. And then we're going to finish the podcast by talking about solids, specifically types of solids. Okay, let's go right into it. So, we learned in the last podcast that intermolecular forces ultimately give rise to the physical properties of substances. And so, let's talk about some of those properties and how they relate to intermolecular forces. First thing we're going to talk about is melting point and boiling point. You guys will oftentimes abbreviate melting point MP and boiling point BP. So, if you're taking notes, doing shorthand notation might help you. Anyway, melting, that's going from a solid to a liquid, and boiling is going from a liquid to a gas, respectively. So what does it mean, or rather, why do substances have different boiling points and melting points? Well, generally speaking, substances that are going to have lower melting points and lower boiling points, that simply means that that particular substance is going to have weaker IMFs between the molecules. And so those weaker IMFs will be more readily broken, and a state change or a state of matter change will occur. Conversely, higher substances with higher melting points and higher boiling points often mean that that particular substance is going to have stronger intermolecular forces, and it's going to take more thermal energy to break those IMFs to overcome and have a state change occur. So what you should see here is that these two variables, or melting point and boiling point, as it relates to weak and strong IMFs, are directly proportional. In other words, for example, the lower the melting point of a substance, the lower the intermolecular forces. And the opposite is true. The higher the melting point or boiling point, the stronger the intermolecular forces. And again, the rationale behind that, you guys, is that more heat energy is going to be required to disrupt and therefore break the intermolecular forces between the molecules of whatever substance you're talking about, with stronger IMFs than weaker ones. So hopefully that's pretty straightforward when it comes to melting point and boiling point. Let's talk about something that you may not remember. This is called vapor pressure. And this is essentially defined as where molecules of a liquid and their ability basically to escape the liquid state into their gaseous state right at the surface interface of the liquid. Okay, and this usually happens when heat is added. And if you go ahead and just take a look at the two flasks that we have in this image, flask A and flask B, you can see that the flask is stoppered, so it's a closed system, and the molecules within this liquid of the flask are going to be captured when they actually convert to the gas. And so that those gas molecules, and you can actually see this and visualize it in flask B, those molecules, those gaseous molecules, are bouncing off the sides of the flask and they're stuck in there. You can see in flask A that the liquid molecules are actually going to escape the surface to become gas molecules. And so you kind of see that more readily in image B. Now, notice in image B, I see arrows pointing downwards back to the liquid state. And that's because those gas molecules, if they're cruising around with enough speed and velocity, when they hit the surface of the liquid, they can actually sometimes go back into their liquid state. So this is a dynamic process that's happening within this flask. So what does it mean when a substance has a low vapor pressure versus a high vapor pressure? Well, let's think about this. A substance that has a lower vapor pressure means that the liquid is going to have really strong IMFs. And that liquid is not going to readily go from that liquid to gas state right at that interface, right? So again, lower vapor pressures mean that the liquid molecules won't readily let them go into their gaseous state. And therefore, the opposite is true. Substances that have high vapor pressure means that that liquid has weak IMFs, and therefore that liquid molecule can more readily go into its gaseous state right at the liquid interface. All right, another vocabulary term, again, lots of vocab, is substances that are said to be volatile are substances that actually are going to evaporate or go from its liquid to gaseous state more readily. And so I would really embrace this word, embrace. You're going to see this come up a lot. And if you could actually use this vocabulary in your free response questions, that's what's going to get your points. So embrace the word volatile. Again, a substance that is said to be volatile rather, is a substance that has a really high vapor pressure and would more readily evaporate. Think about in the last podcast when I was talking about gasoline, that most of you actually can smell it when you're pumping gas in your car at the gas station. Well, that's because, gasoline is more volatile than, say, liquid water. You might recognize the same situation happening when you are using nail polish remover, for those of you who've used it before, to remove nail polish. You can very easily smell it in your small space as you're using it, because that's, again, a highly volatile substance. Now, you can see the proportionality here. This is where we have an indirect or inverse relationship, meaning that if we have a substance with a low vapor pressure, we're going to generally refer to that as a substance that has high or stronger intermolecular forces. And conversely, a substance with high vapor pressure would have weaker IMFs. Okay, and you can see that basically that rationale is given to you more or less. One thing that I wanted to point out here is that the size of these molecules do matter. So in general, substances that have higher molar masses are going to have lower vapor pressures. Does that make sense? Those are bigger molecules, okay? And they're not going to be breaking those intermolecular forces to convert them from their liquid to gas state is going to take a little bit more energy and be a little bit more challenging, making it harder for them to convert. Okay, the third physical property that molecular forces are related to, rather, is density. And density is the degree of compactness in a substance, if you will. It's really a ratio, a derived ratio of mass to volume. And common units that we see in density are grams per mil, or even grams per cubic centimeter. Generally speaking, if you've got a substance with a lower density, they're going to have weaker IMFs. Conversely, if we have a substance that has a higher density, they're going to have stronger IMFs. And I really am not too thrilled with this image that I posted here, but I did like the smiley faces, so there you go. Again, what's our rationale here? Stronger IMFs hold that substance together in a more organized way, a more structured and compact way. You can see the relationship here, you guys. It is, again, a direct relationship. If we have higher density, higher IMFs, or stronger IMFs is probably a better way to say that. Lower density, weaker IMFs. Okay? All righty. Another physical property of substances is surface tension. Now, how does this relate to IMFs? Remember, you guys, surface tension only happens in liquids only. This is one of the reasons why we see, bugs being able to maintain on the surface of a puddle of water, for example. And really, it's defined as the resistance to increase the surface area of whatever liquid you're referring to. Generally speaking, if you have lower surface tension, you're going to have weaker IMFs. And if you have a stronger surface tension between the molecules, you're going to have stronger IMFs. Again, this is directly related. Lower surface tension, weaker IMFs. The stronger surface tension, stronger IMFs. Again, you can read this rationale on your own. It was basically discussed already. The fifth physical property is called capillary action. You've probably learned about this in biology. It's happening across all biological systems, but it's also a very common effect and sometimes when we are using liquids with very narrow tubes in chemistry. Capillary action involves a combination of something we call adhesive forces and cohesive forces. Really quick, ad is the forces between liquid molecules and the force of the container they're being held in. where cohesive forces are going to be the forces within the liquid itself, okay, and just within the liquid itself. And so what happens here is if you introduce a liquid into a small narrow tube, and let's say that tube, like in this picture over here, is made of glass, of course you have to expect that the substance inside the tube might have some effect with the glass itself. That would again be the adhesive forces. And so what we find here, if you look at the image on the right, you can see that a common meniscus, there's actually two types of meniscus that form, and I don't know the plural for meniscus, menisci, I don't know, I'm not sure. But anyway, one is concave and one is convex. Can you guess why? So take a look. I'm going to highlight it one more time. One is concave and one is convex. Why? Well, if you look at the one on the right, okay, the one that I just starred, the meniscus, I'm assuming those are water molecules. Let's make that assumption. The meniscus of those water molecules are actually attracted to the glass of the graduated cylinder, more so, and so it creates this concave kind of effect. Whereas if you look at the image on the left, it has kind of this convex meniscus. And that's because it looks like this substance is probably mercury or something. It's liquid mercury, it appears to be. And the meniscus here means that the mercury molecules themselves are more attracted to each other than the mercury molecules being attracted to the glass. And so you get that kind of concave effect. The stronger the IMF, the stronger the adhesive and cohesive forces. So again, I'm not going to write it. That looks like a direct relationship. Lastly, we have viscosity, and viscosity really is just almost, for lack of a better word, you could almost think of it as the thickness of a substance. But for AP terminology and consideration when you're writing about viscosity, it's simply defined as the resistance to flow. So a substance that is more resistant to flow has stronger IMFs. Think of motor oil, of syrup, of really thick liquid substances. So yes, again, viscosity really is only referring to liquids. Okay, and again, the more viscous, the stronger the IMFs. Again, another direct relationship. So generally speaking, gases, which we're going to focus on in a little bit, they're going to have the weakest IMFs of all states of matter. And that's because gases are moving, they're all over the place, they're far away from each other. Whereas solids and liquids, the intermolecular forces within these types of states of matter are generally going to be stronger. Let's do exercise 5. This asking us to complete the sentence below. There is no word bank provided, so do your best. Go ahead and pause me. You try this first, and then come back and check your answers. The stronger the intermolecular force in the liquid, the higher the boiling point. The state of a substance at room temperature depends on the strength of IMF. And lastly, water molecules in an ice cube are held together by, okay, this is when it would probably be helpful to draw two water molecules and look at the types of intermolecular forces between them. Right off the bat in my head, I know water molecules are polar. So if I have one polar molecule creating an intermolecular force next to another polar molecule, you guys, what type of IMF is that called? You got it. It's a dipole-dipole. Now, we learned in the last podcast that dipole-dipole is the strongest type of IMF, but more specifically, there is a special type of dipole-dipole that we call a hydrogen bond. And in fact, that's what goes in the next space, hydrogen bond. So go ahead and let's read that last sentence together one more time. Water molecules in an ice cube are held together by dipole-dipole forces, or more specifically, hydrogen bonds. Again, remember, hydrogen bond is not a bond. Okay, exercise 6. Describe how boiling points would be affected by IMFs. Again, I'm going to go ahead and jot my answer down. You do the same, come back, and let's compare answers. So I'm describing how boiling points are affected by IMFs. Well, I said that the stronger intermolecular forces between molecules are going to make it more difficult for those molecules to be pulled apart, causing a state change. And therefore, stronger IMFs will result in stronger boiling points. All right, how about exercise 7? Describe how viscosity and surface tension would be affected by IMFs. Remember, viscosity and surface tension is a phenomenon we only see in liquids. So just kind of keep that straight there. And one more time, pause me. You create a response. Remember to use the vocabulary that we're using here, that we're learning rather, and then come back and check your answer. All right. I said surface tension is the resistance of a liquid to spread out, where viscosity is a measure of a substance resistance to flow. And as the strength of intermolecular forces increases, the surface tension and viscosity will also increase. And that's because molecules are more strongly attracted to each other and will be less likely to spread out or to flow. All right, let's try exercise 8. It says list the following substances in order of increasing boiling point. I've been given a list of 6 substances. Notice that this whole unit we're talking about molecular compounds. Okay, I give you a hint. Draw the Lewis dot structure. This allows you to see polarity, and when you see polarity within a molecule, you can also determine the type of IMF. So Lewis dot structure, I can't emphasize how important it is. And maybe what we could do here is this exercise in class. I think this would actually be a good one to do in class as a quick review for IMFs and predicting the boiling point properties. Now, before we end this podcast, let's talk about the types of solids that exist. So we're kind of only going to specifically talk about solids. So this is a little shift in thinking, but all of it's connected, as you'll see eventually in due time. Types of solids, something we're not spending a lot of time talking about that we've already mentioned before, and we got to mention it here, and that is ionic solids, metal and nonmetal, or ions, a cation bound to an anion. And again, when you have this happen, you are going to have a lattice that is formed. Okay, and I put an image right below that you can kind of see an example of a lattice structure between sodium and chlorine. Ionic solids are going to have the strongest attractive forces of all because these are full on charges. All right, they have very high melting points, they have very high boiling points, they have low vapor pressure. They're generally going to be brittle, so if I tried to smash them, they will shatter. Ionic solids can only conduct electricity if you dissolve them in water. And that's because when you do so, you're going to provide that free flow of electrons to complete the electrical current, or to complete the flow of electrons through a circuit. Again, ionic solids, we can go back to Coulomb's law all day long. Coulomb's law is a huge concept, especially for AP. You're going to see it on the test. So it might be worth it at this point to remind yourself in your mind, what is Coulomb's law and what is the relationship between force and charge and force and distance? Okay, moving on, we have another type of solid. We've learned about this, I believe, in the last unit when we talked about the electron C model. Again, all these concepts keep cycling back in. You'll see them coming back and forth all year. Anyway, metallic solids sound like what they are, strictly metals. And these structures are close packed structures, although the actual structure are not really covered in detail on the AP exam. That's right. One understanding they do expect you to know is the general concept and structure of what we call the electron C model. And recall, this is just where we have a regular array of metals and a sea of electrons. And I did put an image for you down below, image A and B. And you can see here the kind of equal distribution of charge occurring inside these metals, these pure metals. Metals are going to have really high melting points, and they're going to be very hard and malleable and ductile. If you don't know what malleable means, it means bendable. Ductile means it has the ability to be formed into a wire. Okay, so one of the things that you should understand is metals are great conductors of electricity. And that is because they have those free electrons available to complete the circuit. And you can see those free electrons up here in the image that I put of a metallic solid. So imagine sending an electrical current through a metal sample. The electrical company really only provides the electrons that make the circuit complete, whereas the wiring found in your house is where that electrical circuit is carried through. So if you think about it, that's all really the electrical companies are doing, is they're just providing a free flow of electrons. And another thing about metallic solids, you guys, we learned about in the last unit is, don't forget, and you'll probably see it on the test, are alloys. I didn't cover it here. Remember, substitutional and interstitial. So if you need to, remind yourself what those alloys are, or what the details of those. Another type of solid that we should talk about are nonmetal solids. That's right, covalent molecules that come together to form solids. There's two classifications here of covalent solids. So this, you need to get straight in your head. We have one called molecular solids and another called network solids. All right. Now, the definitions of molecular solids and network solids are given to you below. So what I'm going to ask you to do, instead of read these to you, is put me on pause, come back, and we will do exercise number 9 that is directly below this. All right, exercise 9, really quick. Let's go ahead and define as either each as either a metallic, ionic, network, or molecular substance, solid. Let's do exercise 9, and it's asking us to classify each of the following substances according to the type of solid it forms. And we just learned about 4 of them. So gold, pure gold, easy. That would be a metallic solid. Okay. Solid carbon dioxide, aka also known as dry ice. Okay, well, this one is actually going to be a network solid. Lithium fluoride. Lithium's a metal. Fluoride is a nonmetal. Aha, that's going to be an ionic solid. And then it looks like krypton, a noble gas, which is nonmetal. And so I know it's going to be molecular in nature. Aha, that's by default the last option. So this would be our molecular solid. All right, you guys, that's going to end it for this podcast. Please let me know if you have any questions. We will go back and work some of the stuff in a little bit more detail in class. Thank you so much.